Well, I can't see anybody beyond the first row, but welcome. Alzheimer's disease, to talk about it in 2013, you have to talk a lot about chemistry and molecules and cells, and I will do that. But it starts and ends with people, and that's what I'm going to do too. This is one of 4 huge canvases in the National Gallery of Art in Washington, D.C., called The Voyage of Life, painted in 1840 by Thomas Cole, who was a landscape painter. The first one shows the child, having just been born, emerging from a dark cave with a guardian angel behind the child on the boat, and the figurehead at the front of the boat holding an hourglass. And I think you can tell that Cole was a landscape painter. There's the little baby, maybe not as charming as the royal baby, but nonetheless, a cute baby. Beautiful landscape, lush, verdant, looks kind of like spring, magnificent mountains that would be familiar pieces of a landscape to most of you. Youth, the baby's grown up. It's a very positive image. The youth doesn't even see the guardian angel behind him, but the riverbed ahead of him, or the river, is calm. There's a beautiful castle in the air, spectacular landscape again, trees and flowers in full bloom. However, if you look closely at the right-hand side of the screen over here, it's a little rockier and the water is a little rougher. Again, something that local residents can appreciate. Manhood is a completely different story. The man is apparently at the mercy of nature, praying. The guardian angel is far away from him. He's being carried into rocky waters. And finally, old age, the last of the 4 canvases, where the man is now aged, the boat is broken down, but it looks like a happy ending. 2 angels, and heaven beckons beyond. There are a couple of points about these paintings that I want to draw your attention to. One is, the man is carried helplessly along. This is not a voyage of life that involves choices. The river cascades down and eventually into the ocean, and he is fundamentally along for the ride. But what's really crucial is the fact that there are angels in every one of these canvases. And that to me, and by the way, these were very, and still are, very popular paintings. I saw these in the National Gallery in Washington about 25 years ago, before I was ever interested in the science of Alzheimer's and aging, and I couldn't take my eyes off them. There's something incredibly powerful about them. But what they say is that in 1840, the idea of aging and death was absolutely suffused with religion. That was what it was all about. It's different today. We live in a secular, scientific age. Our thoughts about aging are inevitably complicated by thoughts of dementia. I want to go back a couple of centuries earlier, actually starting in the late 1600s, coming up through the 19th century. This was a common depiction of the stages of life. Not a voyage, but stages. You start as an infant on the left, you reach the peak at the age of 50, which is somewhat depressing to me. And then you descend down. This individual is 90. There actually is a centenarian in the picture who appears not to be doing all that well. Actually, I wasn't sure I'd ever get a laugh in a talk about Alzheimer's. However, that's good. I think it sets a positive mood. You know, there's something like 6,000 100-year-olds in Canada today. It's the second fastest growing part of the demographic, and it's estimated that by 2060, there could be 38,000 Canadians who are over 100 years old. But again, here's the link. The religious part of this is a little subtler than the voyage of life, but the inevitability is consistent. You were born, you lived, you died. There was no thought about extending life to 150 years, and there was very little depiction or discussion of dementia. And in fact, if this doesn't look like pop culture to you, well, this certainly does. Milton Bradley, the original guy, Milton Bradley, his first game came out in 1860 called The Game of Life. It was played on a checkerboard-like board, and here were the kind of things that could happen to you. It wasn't all good. There was a chance to end up in poverty and or disgrace. But again, an incredibly, in fact, they brought out a new version in the 1990s, which instead of, going to school, ambition, disgrace, it was buy an SUV and, go to private school. So things have changed dramatically. And why? I mean, why do we think about age so significantly differently now than people did in the 1860s and centuries before? Because of this man, whose signature you saw on the screen at the beginning, Alois Alzheimer. He was, in many senses, an unremarkable man, but a very good scientist, very kind to his co-workers, a great family man. He combined two roles, though, and this is really important. He was a clinician, so he dealt with people with mental disabilities, interviewed them, studied them in his clinic. But at the same time, he was part of a fantastic school of microscopists in Germany at the turn of the last century. And so he was very interested in linking the two. You have symptoms, you have some sort of clinical syndrome. Can you look in the brain and see what the connection is? In 1901, he met this woman, Auguste Deter. She came to him, she was 51 years old. Her memory was shot. She was becoming paranoid. She was somewhat incoherent. She was plainly demented. Alzheimer recorded carefully his interview with Auguste Deter, and I'm just going to read you some parts of it because I know that many of you will have heard or seen something like this before. This is 112 years ago. Alzheimer says, "How are you?" She says, "It's always one as the other. Who carried me here? Where are you? At the moment I have temporarily, as I said, I have no means. One simply has to, I don't know myself. I really don't know." Dear me, what is to then? What's your name? Frau Auguste D. Last name? August. What's your husband's name? August, I think. 3 days later, he interviews her again. When were you born? 1800 and... I don't know. What is your husband's profession? Clerk. I'm so confused. I cannot. On what street do you live? I can tell you, Waldemarstrasse. No. When did you marry? I don't know at present. The woman lives on the same floor. Which woman? The woman where were you living? I don't know. So anxious. How many fingers? 3. Are you still anxious? Yes. And then she finishes by saying, just now a child called. Is he there? That was 1901. Alzheimer moved from Frankfurt, where he had met Auguste, to Munich to work with the great psychologist Emile Kraepelin, the guy who coined the terms manic depressive illness and schizophrenia. She died in 2006 in April. He had her brain, sent to him in Munich. He still cared about her, and he was curious about what had happened to her. So he prepared her brain, as you have to, for the light microscope, the tabletop microscope, hardening it, slicing it incredibly thinly with a sharp knife, putting it on microscope slides, thin enough so the light can penetrate and you can see, staining the tissue with stains that bring out the features of the cells. And this is what he saw, which at the moment might seem incomprehensible to you, but in a few minutes I think it will be all too clear. He saw three critical things. First of all, and it's impossible to tell, this is actually the original, one of the original slides. It's hard to tell, but there are many fewer neurons, brain cells, than there should be. Dramatic loss of neurons. Two other crucial features. These dark blobs, which Alzheimer called plaques. They are still called plaques today. The other thing he noted, plaques had been seen by some of his colleagues just before, but the other thing he noted were these odd little squiggles that look like, you know, somebody spilled some ink or something like that. They were all over the brain. Those we now call tangles. And here's the extraordinary thing. In 1906, Alzheimer saw plaques and tangles in Auguste Deterre's brain. They are still the diagnostic feature of Alzheimer's disease. So this is why this was such a dramatic discovery. And I think what's important to say here is this, that since Alzheimer's time, we know much more about plaques, where they come from, how they're made, what they mean, and we know much more about tangles. But at the same time, they are still extremely mysterious. So I want to take those two ideas one at a time, and this is where the biochemistry will come in. There's another, that's a beautiful image of a plaque, and while it's probably too hard to see, there is some sort of structure to it. It's not just a blob. There's actually a central core that's a little bit darker and some fragmentary stuff out here. Here's another picture of one stained so that you can make out much more detail, quite interesting detail, some sort of central aggregation of fibers, and then what you might call flotsam and jetsam of bits of brain cells surrounding it. Just to give you a picture of what we're looking at, this is an artist representation of neurons, brain cells in the brain. Now, we have 86 billion of them. So obviously there are a lot in the ordinary, in the real human brain. It's much more crowded than this. But the features of neurons are always the same. There's a laser, oh, there we go. There's a central round large object, that's the main part of the cell, called the cell body. And there's one major extension going away from the cell that carries the nerve impulse along it and makes contact with another neuron, and so nerve impulses get passed along. These other extensions are receiving messages and carrying them to the main cell body. Now, these you could just see with a tabletop microscope at high power, 1,000 power. Now imagine what I'm going to show you next is just a tiny postage stamp or less area of one of those cells. This is actually a drawing by one of the alumni of the Science Communications Program, Lin Tang, from 3 years ago. And this is where we've cut a cell like this, and we're looking at the surface, the cell membrane, outside the cell, inside the cell. And really what I want to call your attention to is the fact that the surface, the cell membrane, is pretty uniform. This part of it's pretty uniform, sort of fatty, oily layer, but it is punctuated, penetrated, and is home to thousands of molecules that play critical roles in accepting signals that arrive at the cell from the outside, passaging materials from the inside out, signaling, they do everything. Any cell in our bodies is like this. But in neurons, especially in that long process that carries the nerve impulse away, there's one particular molecule that actually is not shown here, but it's a bit like this one. It has an outside piece, the middle of it is actually sitting in the membrane, and then there's an inside piece. It's called amyloid precursor protein. The name's not so important. It's kind of a beautiful molecule because in that full-length version, it does something, nobody's clear what, facilitates something going on in the neuron, but it can also be cut by enzymes into about 4 pieces, and each one of the 4 pieces works as well. So it's an incredibly versatile molecule. Unfortunately, in the wrong circumstances, a piece of the amyloid precursor protein will be cut right here, a short piece. If this is, say, 700 subunits, there's a little piece about 40 long cut out of there called beta amyloid. Beta amyloid, once cut free, aggregates with other beta amyloids and eventually forms the plaques. So beta amyloid is a bad substance to have in the brain. I'm going to show you an animation that might give you a better sense. I know I've been piling up a lot of information here, but let's take a look at this. So before we start, those little pieces would be individual pieces of beta amyloid. And what you're going to see over time in this animation by Alex Tirabasso at the Canadian Museum of Nature is it's all about aggregation. Individual pieces of beta amyloid mean nothing. But when they start to come together to form these twisted helical fibrils, and the process accelerates, as you see it accelerating here, and this, by the way, is outside the neurons. It's not inside. It's in the cytoplasm around them. There are so many of these pieces of beta amyloid that are being made at a tremendous rate that as they start to aggregate, you get into more and bigger pieces, and eventually those pieces come together and form a plaque. Almost exactly like the plaques that I've shown you photographs of. The plaques that you see in Auguste Deterre's brain. So, we know a lot more than Alzheimer could possibly have known. We know that the substance that these plaques are made of, we know that, as he discovered, that they aggregate in the brains of people with Alzheimer's disease. But we're still not totally sure about their role in the production of the disease. So, let me go to the tangles now. That's one actor in this play. The tangles are these little squiggles. This will give you a better idea. Tangles are the most peculiar things. Here's what they're made of. This is a cell, a neuron, that's been dyed in a particular way that you can see its internal skeleton. Those green lines are actually rods called microtubules. They give the neuron its shape. If they weren't there, the neuron would be shapeless. You can see them particularly streaming down this arm. And here's another photograph that's even more spectacular, where this is a neuron, this cell. There's its extension, and you can see it's supported completely by these microtubules. Microtubules, I'll show you another image. They're these light blue extensions. The one on the right is complete and stable. You need that, remember, to maintain the cellular shape of a neuron. The one on the left, can't tell from this diagram, it's either being built or not, or being disaggregated. And you can see there are a lot of other molecules involved. So the raw material are the things that are this color, like there, 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 and so on. But there are all these other actors playing a role in either helping them come together or helping them fall apart. One of those other actors is a protein called tau, T-A-U, Greek letter tau. Tau is a remarkable protein because without it, microtubules wouldn't hold together. So here we have a neuron. We're moving down the neuron, down that long extension, the axon, and you can see inside the microtubule skeletal structure. But here's what I really wanted to show you. This is, again, obviously a very artistic conception of what's going on inside a cell, but these little twisted fibers are the protein tau, and they are holding this microtubular structure together. In an adult brain, if tau starts to lose its grip on the microtubules, and the chemist in our group would like me to say it's hyperphosphorylation, but I'm not going to do that. But if they lose their grip on the microtubules start to fall apart, which is bad for the neuron, and many neurons, but also tau has nowhere to go now, so it accumulates. So there are the fibrils of tau. You can see they're twisted filaments. They've come off those microtubules in the background, and they will start to aggregate, and they will start to form the other bad actor called tangles. This is a rather long animation showing, for some weird reason, this reminds me of a Bruce Willis film that, there's just death and destruction absolutely everywhere. But while this animation would tend to suggest that this is the worst thing that's going on, the loss of microtubules, in fact, what's more important for the symptoms of Alzheimer's is the tau. And here, this again might be slightly overdramatic, but nonetheless, it does cause the death of neurons. So if you lose the tau that's holding the skeleton together, the neuron will die. Here's another image of it. Again, tau tangling together to form a tangle. And get this, so this is a neuron, that purple object, the whole cell, and it's starting to shrink and ends up in that very peculiar shape. And there are the drawings that Alzheimer made of tangles in Auguste Deterre's brain. So that's what he was saying. He was saying the leftovers of neurons that were once live and healthy, but had now been confounded by the aggregation of tau. So plaques and tangles. I just want to take a little sidestep because believe me, I find it somewhat difficult to talk about Alzheimer's in any sort of extended way because it's not all a cheery subject. But let me just tell you something about that protein tau, the microtubule holder. Animals like black bears, any animal that hibernates, has a very weird thing go on in its brain as it enters hibernation. The same thing happens to the neurons in its brain and their microtubules as happens in people with Alzheimer's. The tau falls off and aggregates as tangles. It doesn't matter whether it's a black bear whose body temperature rarely gets below 30 Celsius when it's hibernating, or a Syrian hamster, which becomes much more torpid. Check this out. These are pretty amazing. All the dark staining things are tangles, and this is a Syrian hamster's brain when, two different places in the brain, as it starts to enter hibernation, when it's deep in hibernation, as it starts to awaken, when it's awake. So what's interesting about this is that steps 1, 2, and 3 could be the development of Alzheimer's in a human brain. The difference, of course, is there's a step 4 and 5, where the hibernating animal recovers. Nobody really understands why that should happen or what the purpose of it is. It's also true, though, that in the fetal human brain, tau is not held on tightly to microtubules, and there is a good reason for that. In the fetal brain, new brain cells are being made, and new connections among those brain cells are being created at an incredibly rapid rate. If your neurons were rigid and couldn't grow and couldn't make new connections and were basically as they had been created, you wouldn't be able to create a brain. You have to release the tau, let all that happen, then lock it back on when you've got a secure adult brain. So again, in the fetal human brain it happens, but there's recovery. In humans, there is no such recovery. So there we are, back at Auguste Deterre's brain. And I think, I could have told you much more about the makeup of plaques and their amyloid, tangles and their tau. But I want to turn that around now and give you a sense of what we don't know. And what we don't know about these very things is profound. So for instance, is one more important than the other? I mean, do you first get plaques and that somehow triggers a series of chemical reactions that then produces tau? Well, you know, I could cite 10 experiments that say yes, and I could cite 10 others that say tangles are more important. So for instance, you can use a radioactive labeling technique to actually locate amyloid in a living person, in their brain. And you can track how the load of amyloid grows as a person becomes cognitively less and less able. And they track, right? So you think, okay, clearly, the more amyloid in your brain, the less well off you'll be. But then I could cite another study that shows if you try and correlate the parts of the brain that fail in sequence in Alzheimer's, and I'm going to show you this in a second, what correlates with that progression, that sequence of stages in the brain, the areas of the brain that are affected in a temporal fashion, that doesn't correlate with amyloid at all. It correlates exactly, though, with where tangles are proliferating. And if that isn't confusing enough, because now we don't know whether one is more important than the other, we don't even know which one is really causing the disease, there's plenty of evidence now that it's not even plaques and tangles, it's their forerunners. It's probably true that plaques are there just as kind of refuse of processes that have gone on before. So it's not those giant aggregates of stuff that are critical, it's the little short pieces that precede them. And the same is probably true of tangles. It's those loose pieces of tau spinning around in that animation that are probably causing the disease. One thing this does suggest that is a little bit unsettling is that, all right, you see plaques and tangles in an Alzheimer's brain, but what you have to conclude is the process started much earlier. There is a Colombian extended family who are genetically doomed to get Alzheimer's. It's not even a predisposition. They will get it. And they get it very early, late 40s, early 50s. Amyloid's building up in their brains when they're in their 20s. Now, no one can say, okay, that's a Colombian family with a particular genetic mutation. We can't necessarily apply that to the rest of us. But to say that the Alzheimer's disease process might start 20 years earlier than you actually show symptoms, I don't think anybody in the field would argue with that right now. Come back to that. So what about the progression in the brain? Well, in this animation, there are two critical things to look at. One is the area in purple, and that's, I should say first, we've split the brain in half and we've thrown away the left half. We're looking at the inside right half of the brain. Front is over here on my side, back is over there. And this structure, part of it anyway, right around here, is called the entorhinal cortex. Name's not familiar. That seems to be where the first real loss of brain cells in Alzheimer's starts. The critical thing here is that it is very close to this structure called the hippocampus, which is the structure in our brain that allows us to form new memories. There's a classic case in psychology of a guy named H.M. who had severe epilepsy, so severe they did experimental surgery on him in 1953 and cut out his hippocampus. It worked. He had very few seizures after that time. Unfortunately, he also couldn't form any new memories. And so from 1953, when he had the surgery, until 2005 or 6, when he died, or 8, he lived a good long life. He lived in a perpetual now. Couldn't remember what he had for breakfast or lunch, couldn't remember why he would be here in the audience. And every day was like that. So the hippocampus is essential for memory. But the disease starts here. It spreads. Nobody's really clear how, but somehow those either plaques or tangles or their predecessors can move from one neuron to the next. They get into the hippocampus. What do you get? Memory deficits. First significant sign of Alzheimer's. And then, because the human brain is beautifully wired, the disease will move from the hippocampus to the frontal cortex, and the rest of the cortex, and the rest of the brain. So we know the progression of spread, but there's two ways of looking at that. So this is one way. I've slowed this down. This imaging shows you that blue and purple are bad. Many neurons have died in the blue and purple areas. This is how it spreads. By the way, what's tracking here in the colors is where the tangles are. Like I said, tangles seem to track the development of the disease. What's shocking about this is that the whole duration of this animation that I'm showing you, which was gathered from a number of Alzheimer's patients having MRIs, is that the total change, and I'm going to show you what this brain looked like when we started over here on the left, the total degree of change that you see occurred over 1.5 to 2 years. And so there now is a vast amount of neuronal death. And that person would not be in good shape. That's how it started, 1.5 to 2 years. So once it's true that once the disease takes hold, it's inexorable, and sometimes it takes a little longer, sometimes it takes a little shorter, but it is kind of inevitable. Now, I said at the beginning, you've got to look at this at many scales. Molecules, I've already done that. Cells, yes. Brains, yes. People. I'm going to show you a series of self-portraits by a painter named Bill Utermohlen, who was born in 1933, was told when he was in his mid-60s, he was diagnosed as having Alzheimer's. That was in the mid-90s. And he proceeded to set out to paint a series of self-portraits as a way of expressing what he felt. And I think that rather than discuss these, I will just show them to you. The first one you're going to see was painted in the 60s when he was in his 30s. There he is. And then the rest of these are his self-portraits while he was becoming demented. It's impossible to know what it's like. A series of self-portraits like that maybe gives us a clue. Having loved ones or friends go through it gives us another clue. But I think it's one of the frustrating and somewhat demoralizing things about Alzheimer's disease is that, if somebody breaks their leg, you can empathize with their pain. It's a little hard to know how to empathize with a man who's going through that. Now, this is going to sound funny, but there might be some good news. And that comes out of a study, one of my favorite scientific studies, long-term scientific studies, called the Nun Study, which actually has now become the Religious Orders Study. to be gender inclusive. And this was started in the early 90s. 678 nuns of the School Sisters of Notre Dame enrolled in this study. The goal was to give them psychological tests every year, MRIs, and autopsy their brains at death. Two really remarkable results from this study. One is based on the odd fact that when young women, 20 to 22 years old, sought admission to the order, they had to write an essay explaining why they wanted to join. A number of these essays were collected and kept until the 22-year-old was 80 or 90. And then they studied them for something called idea density. How many ideas, like little Matryoshka dolls, were nestled in the sentences that they wrote? So, for instance, I was born in Eau Claire, Wisconsin on May 24th, 1913, and was baptized in St. James Church. So actually there are 7 ideas in that sentence if you do this idea density analysis. I was born, that's one. Born in Eau Claire, Wisconsin, that's another. Born on May 24th, 1913. And in this particular case, 7 ideas in 18 words, that's 3.9 for every 10 words. That's an idea density of 3.9. 3.9 on the low side. Here's another. The happiest day of my life so far was my first communion day, which was in June 1920, when I was but 8 years of age. And 4 years later, in the same month, I was confirmed by Bishop D.D. McGavick. In 1926, I was graduated from the 8th grade, and now my great desire of entering the convent was soon to be gratified. Idea density 8.6, not 3.9. Those nuns who went on to become demented had low idea density scores. Those who resisted dementia had high idea density scores in the range that I've described, 3, 4, 6 to 8. They were 22 years old when they wrote that. What is going on? Now, you know, your first thought might be, are you telling me that Alzheimer's disease starts when you're 20 years old? Not necessarily. It could be, in fact, that something about the brain, as reflected in these essays, protects those with high idea densities and does not protect those with low. That something could be called brain reserve. Here's another example from the same nun study. Sister Mary. Sister Mary was 101 when she died. She, on her last psychological test, which was about, I think, 4 months before she died, she scored in the normal range. At her age, they expected her score to be 4. It was 27. Autopsied her brain, full of plaques and tangles. Full. So, you know, if you'd taken slices of her brain and showed them to an Alzheimer expert, he or she would have said that person was demented. She was not demented. Is that brain reserve some sort of protection against the ravages of the disease? So, here's what brain reserve might be. And honestly, nobody knows yet. Could it be that these people just had bigger brains to start with, more neurons, have lost tons of them, but still have a fair number, and so they're not demented? That's one possibility. Another might be that it's not so much the number of neurons they have, but the circuits that they've formed and their flexibility in dealing with problems or dealing with language that, you know, if this circuit stops working well because it's losing neurons, well, you can reroute things around this way. Or maybe even some neurons grow back. You know, 10 years ago, if I'd given this talk, I would have said, everybody knows the human brain doesn't generate new neurons. That's not true. They do. We do, especially in the hippocampus. Brain reserve correlates with education. There was a set of IQ tests given to Scottish children in grade 6 in 1931. The highest IQ kids were less likely to become demented by the 1990s and 2000s. The lower IQ kids were. How far you went in school? High school? Did you finish high school? Are you a high school graduate? Are you a college graduate? Did you do postgraduate studies? The higher you go up that scale, it seems the less likely to become demented you are. What's your occupation? Is it one that demands a lot of brain work or not? Again, the correlation. And let me just point out one thing about this, because I said it's sort of good news. Yeah, but a little bit good news. These three brains represent three people who are psychologically, cognitively exactly equivalent. Not one of these is more, more intellectually able than any of the others. Not one of them is more demented. This one up here, the blue shows the degree of disease, plaques, tangles, loss of neurons. So this upper brain has a lot of damage. This one, less. This one, less. This person went beyond high school. This person is a high school grad. This person didn't finish high school. So here's what brain reserve is doing. It's, even though you have pathology in your brain, your education is protecting you against the symptoms of that pathology. So you have plaques and tangles, but you're still okay. But there is a tipping point, and this has been seen a lot, so that that person whose brain is at the top will get to a point where they have no more brain reserve. There's just too much damage. And they will decline faster than the person whose brain is at the bottom. So you do see this kind of twofold decline. People have brain reserve, resist disease, and then plummet. Those that got Alzheimer's earlier decline slowly. Unfortunately, they reach the same point at some point later. So, maybe it's better. Like, I honestly think it'd be better to hang on, and then have it go quickly if I were so unlucky. I just want to add one more thought about this idea of brain reserve, because I haven't fully explored it yet, but it is pretty extraordinary. So for instance, there's a correlation between how well you score, or how conscientious you are, and whether you'll become demented. The more conscientious you are, the more you persevere, the more you set yourself goals and finish them, the less lazy you are, the more you meet your deadlines, all of that stuff protects you against dementia. And when I heard that, I immediately recalled some of the stuff I'd read about 200 and 300 years ago when people were admonished to live a good Christian life. What was a significant part of that life? It was being diligent, going to church, being a responsible person, all things that could be called conscientiousness. And so, even though the purpose, the stated purpose for acting that way then was you'll get to heaven on, the boat, maybe in a kind of roundabout way, the advice that people were giving actually might allow you to lead a longer and healthier life. I mean, I can tell you, brain reserve over the next 10 years is going to become a hugely important topic. Now, let's say you want to catch up on your brain reserve, which would be, an attractive idea. How can you do that? I'm not going to talk about diet. Clearly, diet plays an issue. If you're obese, if you're diabetic, if you're not eating properly, if you have heart disease, all of these things predispose you to Alzheimer's disease. I want to focus instead on mental exercise and physical exercise, and I'm not going to go through a huge amount of detail here except to say this. There was a big study by the Ontario Brain Institute earlier this year where they looked at every scientific study of the effects of mental exercise. People, get into their 60s, start doing Sudoku, because you never know, it might help. Do a little yoga, too. So mental exercise, physical exercise. And here's what they said. Ideally, do both. If you can't do both, if you have to pick one, physical exercise is the more important. And when I say physical exercise, I mean 45 minutes of kind of not fast walking, but a good pace of walking every day. 45 minutes. It looks like that amount of exercise, and you can pick it up later in life, can prevent about 14%. 14% of those people who might have gone on to get Alzheimer's disease will not get it. Now, of course, when people say they will not get it, what it really usually means is you'll die of something else first. Because the stats, oh, and I thought people were being given out, did you get a little program? Oh, good, okay. Because I think I say it in there that 10% of people over 65, 50% of people over 85 get Alzheimer's. I mean, this is why this research is important, because the healthcare costs, were it to continue at the rate it is in North America and other developed countries, the healthcare costs would simply be incalculable. Thank you very much.